Okay, thanks for having me. This is I've been to all of them, including in London, and a terrific conference. And very convenient for me now. I like it better than London, because look how, we're so close. So we're just across the border in Potsdam, New York, right across from Cornwall, if you know Canada. Ottawa is very close, about an hour and a half to Ottawa. So this is joint work with two postdocs, but one's a former student. He's at Yale now. Sudham is at Yale. Jeremy Fish is at Potsdam, and then me. Clarkson University, and I lead the Clarkson Center for Complex System Science. So it's about density estimation method for estimating transfer operators. And there's a double entendre, because I'm going to use kernel density estimation, which is a method from statistics, essentially for estimating the kernel of the operator. So kernel's used twice in two different ways. It's a counterpoint to a classic data-driven method for estimating transfer operators, which is due to Ulam. He published a book of conjectures in 1960, and one page is what we call the Ulam method for estimating transfer operators by essentially estimating, just dividing the space into little boxes and estimating points by the invariant measure that fall in the boxes and transfer between them. And I'm going to recast that as a data estimation problem by histogram method, which has an error analysis. And I'm going to suggest actually it might be nice to do that by kernel density estimation method instead. And anyway, it's the error analysis that's key. And that's an amazing book by Ulam. Page after page after page is full of conjectures. That particular conjecture that estimate converges weakly as the boxes refine, that was proved, I think, in 1976 by York and T.Y. Lee. Okay, a little bit of background instructional material. So it's for estimating the Frobenius-Perron operator. The Frobenius-Perron operator was a very famous operator, but somehow it got overshadowed, I think, in recent years by the Koopman operator. So Koopman and Frobenius-Perron are almost the same operator. They're adjoints of each other. One's the push forward, the other one's the pull back. So I'm going to contrast those. And it seemed like all through like 2000 to like 2015 or so, the Frobenius-Perron people had their own conference for finding things like invariant measure, coherence sets, and like this through eigenfunctions. And then separately, the Koopman people had their own conference, eventually through DMD methods. And then we started using the two operators together, often for finding coherent sets. And then the two communities also essentially merged, because if P is the operator, you do P star P, then you get something like a covariance version of the matrix, of the operator. Okay, so what is Frobenius-Perron? Suppose, this is my pedagogy slide. Suppose you have a map like logistic map. So this is logistic map. If I iterate one initial condition, we know how to iterate. You just plug it in and plug it in and plug it in and plug it in. But another way to think of the map is by plugging in not one initial condition, but like a billion initial conditions at once that you distribute by some distribution. And if I plug in the whole distribution at once, all the points move, but the distribution gives you some new distribution when I look at where the points land after one iterate. And the operator that does that is the Frobenius-Perron operator. Acts on the space of distributions. Often it's cast in terms of L1 over the space, but it also can be cast in terms of L2 if you want to do matrix operations. So a lot of the stuff that's done with the data-driven side of the house is done in L2. It's a smaller space, but it's a good place to work with matrix computations and eigenvectors and so forth as representing eigenfunctions. So one thing to ask is, where do all those points settle? In the long run, the distribution, you end up getting this distribution, which you can find in closed form for this map. It's rho is equal to 1 over pi squared of x1 minus x. Another map, the tent map, it's a very similar map, they're topologically conjugate. If you sprinkle a billion initial conditions uniformly, it turns out that even though the points move, you still get the uniform distribution. It's the invariant density, but it's actually the absolutely continuous invariant density. There's infinitely many other invariant densities, but there's only one absolutely continuous invariant density for this guy. The other invariant densities correspond to periodic orbits. You can have delta functions over periodic orbits or convex sums of those. And you can also have even more. You can have distributions over invariant Cantor sets, and there's these things called unstable chaotic saddles. This is a little object that I invented, and it's in a few papers of mine around 2000, it's in my old book. I call it a quad web, which is just a picture way of showing what it means to be conjugate between two maps. So here's a picture of the logistic map. Here's a picture of the tent map on the side, and they're conjugate through a cosine square function. And so you map up to the transformation, up to the map, over the transformation, and then up, or I can go up to the transformation over, and you end up in the same place. So you get little squares, which is just this statement of conjugacy. So it's a nice picture way of showing conjugacy. I call it quad web to mimic the idea of cobweb. So this, I just said this stuff. Logistic map, a time series of one initial condition, a chaotic map, but a histogram of many initial conditions, histogrammed, and you get, this is 10 to the 5 initial conditions by histogram, gives you this singular function. And for tent map, it gives you uniform after a long number of iterates. So how do you show distributions? Well, the easiest thing off the shelf is to show histograms, and that's what that is. But then there's the idea, well, how big should I make the squares for the histograms? So I learned back as a grad student, you should choose the number of squares to be roughly the square root of the number of samples. But there's a better way of doing that analysis, and that's what's in this talk. Just going to skip through this guy real fast. But how do you derive a Frobenius-Perron operator? Well, Frobenius-Perron operator for a map that maps from a space X to X is another map I call P. P maps from L1 to L1 over the same space. L1 is where the densities live. And I say, well, how should the densities live? It should be a statement of conservation of initial conditions. So whatever the density was initially over any measurable set, say on a preimage of the set, where does that set go to? Integrate over that, whatever the new density will be. And it just says, this picture, what's the density here? It is where all the points that landed in it came from in preimage. And the preimage often will have multiple branches for a map like this. And you notice that when I do this preimage thing, that the sets are compressed in this case by the slope, and that comes out through the calculus. So if I take the derivatives of both sides of this equation, you kind of untrap the operator side. And if I think over one branch, I can break this guy up, and then fundamental theorem of calculus and the derivative of the preimage, you end up getting 1 over the derivative, which is another form of the Frobenius-Perron operator. The Frobenius-Perron operator of the density at a point x is equal to the density of what it used to be at the preimage point, but it's scaled by the derivative. And it's all in the picture. So it's a nice closed form operator, and very few times you can actually compute the densities in closed form. There are very few maps where you can actually do that. This one you can. So it turns out that, well, we know the preimage of logistic map. It's a quadratic formula in 2 branches. And so if I map forward a density across the 2 preimages, this is actually the operator in closed form as a symbolic object. What's it good for? You can plug in the invariant density, and the arithmetic will show you get the same thing back on both sides. How do you guess this? You guess it by an easier map. It's very easy to just guess and then check that the invariant density for tent map is uniform, the uniform density, and then you can transform that through the conjugacy function. Okay, on to data-driven. In 1960, Ulam published this. I don't know when he thought of it, but he published this in that nice book of conjectures. So if I think of that operator as being a finite rank estimate, here's a nice finite rank estimate of the operator as a matrix. And I say, collect my long orbit of points, xk, and I ask, how many points land in a square qj? And then on the next step, we'll land in a square qi, and I'll call that aij, but scale by the number of guys that were in qj in the first place. And this is a picture version of this thing. I maps across several squares, and a certain fraction will land in j. So you can think of it as like, that is like a Monte Carlo estimate of an integration that says integrate over these guys. as if they're characteristic functions over each square. And that's one way to think of it. But I'm gonna recast this as a statistics problem in a second. There's a scenario where you get exact finite rank descriptions of the matrix, of the operator. The operator itself is finite rank with the right partition. It's a scenario called Markov maps. So a one-dimensional Markov map is one where you have these three properties that I'm going to call out in pictures. So a map is Markov if it has a Markov partition. A Markov partition is a partition which is a set of disjoint open sets such that their closures cover. That's what the first guy says. The interiors don't overlap, but the most important property is that when I map one of them, it maps exactly across a union of the other guy's closure. That just means like this guy maps exactly across a few of the guys. So if it's piecewise linear, you just kind of connect the dots of the corners. Is there such a partition? And I was very interested in these kind of partitions for a long time. And eventually my interest kind of like, I did everything I could do, but it was about symbol dynamics. These are the kind of partitions that generate nice symbol dynamics where the representations are finite rank. And I came to all the operator stuff from symbol dynamics once upon a time. And you can think of symbol dynamics as a grammar where you have these transition matrices, but you don't worry about the weights. You think of the weights as uniform. If you take, well, what's the relative number of guys that move around according to the weights, then you get stochastic matrices. And eigenvalues and eigenvectors and so forth represent eigenfunctions. This is back when I was looking for generating partitions. I drew this picture, this, and this, in a paper on something else in 1998. It was about symbol dynamics. And I took the Hénon map, which is this map, a diffeomorphism of the plane, and I thought about what would happen if I divided the space up into little squares. I'm not showing the squares where there's not an invariant set. Divide the space up into little squares, and instead of keeping the squares where they are embedded in the space, you think of which square goes to which other square. So I kind of blew apart the attractor. So where'd my 14 go? 14's here somewhere. There's 14. Oh, it got cut off by that. Where's 12? 12. Well, here's 13. 13's here. And 13, this little bit is this little bit. And 13 has some points that go to 10, and some points go to 9. 13, some points go to 10, and some points go to 9. And if I kept track of the relative numbers, I would be doing Ulam's method. Then there's the generating partition story, and there's a lot behind the phrase generating. It generates the topology that is the underlying, probably standard topology of the system. But anyway, there was a conjecture by Svetanovich a number of years ago that says the generating partition, which generates the symbol dynamics, should connect the dots between homoclinic tangencies, and there'll be infinitely many. And here's an estimate of it, this horizontal line, and all images and pre-images, and I labeled the symbols accordingly under iteration. And anyway, I could think of that as a transition matrix. A counterpoint to that, it's a different transition matrix because somehow this is more efficient. But then what about this thing? This is what Ulam said. So now I'm going to start bringing it to, okay, one more statement about Ulam. What did Ulam actually say? Ulam said, make this make this estimate based on samples of orbits, but now I'm actually describing it differently. I'm saying, what's the relative measure of I that eventually hits J, which is, for a one-dimensional map, it looks like this. I'm drawing one-dimensional maps because I can draw both the set and its image at the same time, but this is not in the least restricted to one dimension. It's restricted to low dimension because keeping track of the boxes in high dimensions is a nuisance. It has to do with the box counting dimension of whether you can computationally keep it. So capture this thing, whether by samples or by like measuring relative size of sets directly by an integration method. And then once you have this thing, compute its dominant eigenvector. It's a stochastic matrix. The dominant eigenvector will correspond to the eigenvalue 1, and the dominant eigenvector will describe the invariant density. One eigenvector will describe the invariant density. The other eigenvector, the left eigenvector, will describe just that its row sums to 1, so it'll all be 1s. So capture this guy, and as I refine, it will converge in varying density. That was the Ulam conjecture. And as I said, it was proved by T.Y. Lee in 1976 under certain conditions of the map by arguments, boundary variation arguments. And they're not really constructive to what we're doing here. So many papers after that started interpreting that as a Galerkin projection, and that's useful for what I'm going to do today. So as a Galerkin projection, you can say I've got a projection from the space to linear subspace. I said L1 here, but way I'm discussing today, I really should say L2. Suppose I have basis functions, phi, in the set of functions. The finite linear span of those guys I'll call this, and so I have a projection in that space. And I'll say the density is a finite linear combination of those basis functions. If I choose those basis functions to be characteristic functions, so 0, 1 functions over the grid, I can think of this as representing the Ulam method. But when I do it that way, when you do Galerkin, you say, okay, how does my operator act on one of the functions? And if I had an inner product to one of the other basis functions, and it just now is a double integration, because it turns out this guy's an integration too, the Frobenius component operator. I'll show you that in a second. I showed it to you in the sum version, but you can also think of it as an integration. And this will represent the matrix. And so I'll show you a summary slide, but I showed you 3 different versions of what is Ulam's method. And I like this one very much. It leads to a lot of the mathematics, where the proof came from, of the convergence. Oh, and I also like it very much because it suggests you can use other basis functions besides characteristic functions. In fact, I want to mention that. I mentioned a scenario where this is exact. This is exact in terms of characteristic functions as basis functions. Actually, once upon a time in like 2008, I wrote a paper with my friends Gora Struska and Karl Zaskowski in Poland, which we called basis Markov transition. So we had other kinds of basis functions entirely we're able to construct where you got finite rank estimates, but they weren't characteristic functions. It's like a symbol dynamics. Okay, just a mention of Koopman operator. I've been writing a book on data-driven methods, and this is a picture in my book. When I think of Koopman, I think of the rubber ducky contest in my town that runs every summer, and they have them in a lot of towns. They dump a whole bunch of rubber duckies in the river, and the rubber duckies float downstream, and they all have numbers on them. And whichever ducky gets to the finish line first, then you win the lottery. You win the whole pile of money. So if I think of each rubber ducky, it had a temperature probe on it, or some kind of probe, because that's the story of Koopman. It's about observable function, so why not temperature? So if I put a temperature probe on each rubber ducky, then as it moves to the water, it would read different temperatures. So I can report the temperature wherever it is, but actually what I want to do is, as soon as I drop it in the water, I want to ask the question, what will be the temperature after it goes downstream for like 1 minute? And I'll tell you that temperature now. So I want to report the temperature downstream, and that's the Koopman operator. It says, have an observation function g, temperature, and at x, I want to tell you what g is downstream at st of x, and I'm going to tell you the answer over here. So if g is a scalar field across the river, the temperature, then applying Koopman operator is a distortion of that function, gives you a new function. And, okay, so this is the formalism behind it, right? A dynamical system or a map or a flow, you can do it both ways. A set of observation functions and the composition function. G can be measured at x, but instead of measuring g at x, I'm going to measure g downstream. This is composition. Sometimes Koopman's called a composition function. So it's this picture. A neat thing is you can represent this operator in the delta function form, and this says exactly the same thing if you're used to Dirac delta function. So integrate out g, but select it at st of x by delta function. Right, so that is the same thing I just said. Now, I claim they're adjoints, so in a bilinear form, it's just going to push the k across to the other side. And that corresponds to, so it's integration, corresponds to flipping the role of the x and the y in the integration. So if you flip the role, that's the only thing different between these two integrals. The x and the y flip roles. And this, as a delta function, says select an f, but these are going to be densities now. Select an f at something having to do with upstream, but report it back. So it ends up being a pull back. So if you work with properties of integrals, you end up getting exactly that thing, f divided by the derivative of s. So anyway, they're adjoints of each other. I'm going to skip that one. Okay, so here's the three versions of Ulam, and now on to density estimation in a second. So it's always this picture. One version of Ulam is you say, take a box and look where it came from and scale it. And another version says, think of characteristic functions and integrate the action of the operator and scale it. And another version says, just count points. And the just count points, you can show, I'm not doing a lot of work of that here, you can show that this and this are essentially the same thing. It's like a Monte Carlo integration, we just sprinkle points. But now I'm going to show you a different version of the story. I'm going to describe this as histogram method. I'm going to do it for maps like this because I need some regularization anyway. And I claim that when you work on the computer, there's always a little bit of regularization, meaning you never work with a delta function. There's always a little bit of noise, even if it's round-off error. But the technicals suggest that I can't work exactly with the map, and I can't work with exactly with the delta function. So I'm going to pretend that my map has a little bit of noise added. So when you add a little bit of noise to a map that works in a finite domain, so many people add Gaussian noise. When you add Gaussian noise, your operator estimate has those tails that you end up not looking at, and those tails end up corresponding to a spectrum that maybe should have some points on the unit circle, but they're all just a little bit inside the unit circle because you're throwing away some of the measure. So there's a little technical fix, to make all my analysis work. I'm not actually going to work with Gaussians. I'm going to work with, or other distributions like that. I'm going to work with what's called truncated distributions, so truncated normal. And the truncated normal has this notation, but it just simply means, that stuff in the tail, throw it back in and scale it correctly. And so this distribution is, right here, is the truncated normal. You end up getting this ERF function. So the picture of a truncated normal might be like this dash line, which looks very normal-like, except there's a little bit more weight in the tails. And if the distribution has a mean that's not centered, then you see I get this nice tail that reminds me to my eyeball of a normal, but on the other side is very not normal. It's a little technical thing. But anyway, the logistic map with a little bit of noise looks like this. So little noise that you can't see the noise, but a little more noise. See, it fuzzes out. The important point is you see the top up here, I don't have stuff getting thrown out of the unit interval, which is so important if you know a logistic map or other maps like it, because once you throw it out the unit interval, it starts marching off to minus infinity, and the invariant density of that map is very different. So you do need to respect your density, your invariant sets and so forth. That's a general story. Okay, so the kernel of the Frobenius-Prone operator is essentially a distribution in its own right. That's one of the messages I want to say. So this is the Frobenius-Prone operator under a noisy kernel. So instead of the delta function, you just put whatever the distribution is there. And with the distribution being the one that was truncated normal, here's pictures of the kernel for logistic. Again, I'm working logistic a lot, so I can show you the pictures. But nothing about this says you have to work in one dimension. So with a little bit of noise, you get what looks very delta function-like, but a little bit smooth. But you do have these little hooked tails. So actually, I've seen so many papers in this kind of stuff, and people often don't have these hooked tails at the edges, which tells me they're not properly handling the noise. And then their eigenvalues won't end up right. So you just with your eye, you can see immediately whether someone's doing it right or they're doing it wrong. So here's a very small standard deviation and less, more and more and more. And by the time you get to more, the hooks become less pronounced. Okay, so I'm actually was taking the distribution and just plotting it by plotting lots of points because I have them closed form. So how would I capture these guys if I was doing a data-driven method? If I was doing a data-driven method, well, I'm just saying which points x eventually land in x in the next image of x, again, just like I was doing with Ulam's method. And Ulam's method, well, I'm just essentially making histograms. I'm making histograms of that distribution, whether it be the zero noise version, which I claim is never really zero noise, or really a noisy version. And here's a few different histograms for various different box sizes, but instead of box size, I'm going to try to say bandwidth, because bandwidth is going to be the same language you use in kernel density estimation. So box size is 1 over the bandwidth, or rather bandwidth is 1 over the box size. So here's 100, and here's 40, and so forth. And from this kernel, I can think of pretending it's a matrix and finding eigenvectors. And this is the dominant eigenvector as boxes, but not really boxes, they're now cells. And I drew over at the red, the true distribution. And you can see the true distribution becomes better and better with more and more samples and more boxes. And those two should go together. You don't just take both limits to infinity separately. I'm sorry, I'm forgetting one thing to say, but I'll come back, I'll circle back. Okay. Here's the thing I want to say. So here's the kernel, here's the delta function form, or should I say nu, and I can actually think of this as a matrix times a vector, rho, not literally a vector, but it's summing across elements y, but a continuum of y's, because it's an operator, it's a finite ring, it's a infinite dimensional operator, but I'm estimating it by matrix. So pretend this is a matrix operation. And if I pretend this is a matrix operation, I can actually think of this in like in Bayesian language. So in Bayesian language, a Bayesian interpretation of a transfer operator, so usually in Bayesian language, you make this flip. You say posterior equals likelihood times prior, and you don't bother scaling out by the correct distribution because you just want proportionality. But in this case, if it's a stochastic matrix, you don't even need to. So what you usually do is you say data conditioned on parameters times your prior distribution on parameters can be turned into a statement of what's your distribution on parameters given the data. And I claim this does that. Well, I'm just going to do it by analogy. You can make this a bit more strict, which I did in my paper. But by analogy, you can say, you know what? Probability of transition from I to J is a conditional probability that X lands in I, conditioned on the image, I always say prime, the image lands in J. So this is like a conditional probability. But this probability says, Ulam, that measure thing is, what's the measure or the probability that X is in I and its image is in J, scaled by the number of guys that were in I. And doesn't that look awfully a lot like the kind of statement you would make in distributions for building a conditional distribution? And you can estimate this guy by the box thing or the number of points in boxes thing as an estimator. But from these things, I'm going to just inspect the different components. I'm going to say probability X is in I and X prime is in J. I can estimate that by the counts. That's the numerator. And the denominator is this probability. Or I can say probability, the marginalized, that under the new distribution after the image of X primes is it's a marginalizing out the joint distribution X prime and X based on all the guys X prime which are f of x's. So I can think of this as marginalizing, and this was the operator I showed you earlier. And so comparing that to the conditionals, I'm going to start calling this distribution, the joint distribution, X prime given X times probability of X. So X prime given X, so X prime given X is going to be 1 over the derivative and then the delta function part. So each of these two parts I can think of as their own distributions. It just has a Bayesian framework or framing. Okay, on to density estimation, classical theory of density estimation. So in the theory of density estimation, as a empirical statistician would do, it's not good enough to say, here's your estimate. You want to know what's quality of estimate. So in the quality of estimate, first you formulate the phrasing of it, and then I'm going to do an analysis of biases and an analysis of variance. So the boxes are as usual. You just divide up the space into a bunch of boxes by k. So if it's a line, there's just k of them. If it was a square, you do k by k and so forth. And the density estimator, let's put a line over it. The density estimator due to n samples and k boxes is the number of guys in I divided by n divided by the measure of I, which I said in characteristic function framework is like this. So the estimator is exactly what we're saying before, but here comes the part you may not be familiar with, but it's standard fare in this little sub area of statistics. What's the bias? The bias of the estimator is always the expectation of the estimator minus the true. And you can say that there's a point x squiggle in the domain that makes this right. And that's bounded by, now comes a little bit of fundamental theorem of calculus. So this was mean value theorem, because that's an integration. And then the next one is basically fundamental theorem of, this is fundamental theorem of calculus because it's an integral. And then this one's a mean value theorem. It's bounded by the derivative someplace in the domain and the distance between the points. So you have this thing which you can bound, which is the largest value of the derivative in the domain. So the bias ends up being that estimate C1 divided by K. So it scales as 1 over K. That's all I really care about here. Scales as something 1 over K and something having to do with the derivative. And remember when I smooth the distributions? This is one of the reasons you have to do that. Because the 2 distribution was 1 over pi squared of x, 1 minus x, has a singularity, and then that derivative would be unbounded. But I say don't worry about it because you're never actually working with the exact map. You're always a little bit of smoothing. So this derivative will end up being bounded in the noisy case. Okay, that's bias. Variance. Variance you can work out in a similar way. That the usual stuff for variance. There is some cute calculus involved, but it works out to be, I'm going to do this in more detail in the density estimation side. Works out to be, again, the k times density at some point in the domain plus, again, density at some point in the domain square divided by n. So it's dominated by k over n. So again, a k over n. So the error, the mean square error, is bias squared plus variance, and just throwing in those 2 terms is less than or equal to something 1 over k squared and k over n. Those are the 2 dominating terms. Good. I'm going to compare that in a second to a different version of density estimation, kernel density estimation. Kernel density estimation is another very nice way to estimate densities, and in fact, it ends up having better error performance. So what's the error performance? You only choose one over the other based on what you want to do for error performance. Did I pick up the first slide? Yeah. So kernel density estimation says, okay, sprinkle a bunch of points on the domain, and around each point, think of there being a distribution, some nice distribution. There's a whole bunch of selection of nice distributions to choose as the kernel, but I'll just speak in terms of a Gaussian. So put a Gaussian with some bandwidth, meaning a standard deviation around it, and if the points are nearby, lots of points nearby, you'll have a sum of Gaussians nearby, and it'll build up a nice shape, nice distribution. And when there's few points, you'll have very little space. So here's a picture of a bunch of points sprinkled in 0 to 1. This has nothing to do with dynamics. This is just showing density estimation. A whole bunch of points sprinkled in a linear domain, and adding up a bunch of Gaussians gives the blue curve as a convex sum, and with the true distribution being the red curve. And you can see they're very close. Okay, 5 minutes. And then with less bandwidth, it ends up being more so smaller bandwidth, it ends up being more rough. So here's this guy for this estimator, and here's the same thing for histograms, and histograms ends up being very rough compared to the kernel density estimator, and that's just by experiment. By analysis, you can do the same stuff front to back. So I did such a good job on the pedagogy, I went too slow to show you this in great detail. I'm sorry about that, but it's very standard stuff. So you do bias, you have to do bias squared plus variance, and you can compute both those things in closed form estimators. So the bias is expectation of your estimator minus the truth. These are just integrals, it's standard stuff. Together with the Taylor series on the distribution, you could eventually compute that the bias is, okay, delta is the bandwidth. So bandwidth squared times something that has to do with moments. And that's good up to something at least delta squared. And derivative of the densities. And the variance is the same kind of thing. And you can bound it by, you could eventually bound it by 1 over n delta. So that's the dominating terms. The bandwidth and n. And remember, for the other, it was k over n. So it's very similar. So the mean square error is the two guys summed, will square, and the other way sum, up to delta to the 4 and 1 over delta n minus 1. So the estimator is dominated by terms 1 over delta squared, the bandwidth, that's just like the Gaussian's bandwidth, and delta over to minus n. So comparing the two, histograms, we got this, 1 over k squared, k over n. And kernel density estimation, we got delta to the 4 and 1 over delta n. And for many scenarios, this does better, but to actually compare them, you should say, you know what, let me give them both the best shot. So you can say optimize each one individually, show me the best bandwidth for the data set size for the particular problem. And that's an optimization problem you can carry out. You end up getting that for kernel density estimation, that optimal bandwidth is C over n to the 1/5, a funny number. Question? And so far, this estimator is in one dimension. And then this one down here, this is arbitrary dimension. So in one dimension, it's C over n to the 1/5. So most of the analysis I showed you didn't really have much to do with dimension until you get to this last stage, the optimization stage. Otherwise, it's just carrying through, pushing integrals through the mean value theorem is still nice. Anyway, the arbitrary dimension version is n to the 1 over 4 plus d, where d is the dimension. And for histograms, you end up getting some funny constants, n to the 1/3. So plugging those into these expressions, you eventually get the punchline. So for kernel density estimation, it's 1 over n to the 4/5 in one dimension. And in n dimensions, it's similar. And in histograms, it's 1 over n to the 2/3. So you can see for the data set size, you actually get different things, and usually kernel density estimation outperforms significantly. And the rest is just experiments to show that. And then you can use those estimators to compute eigenvalues and eigenvectors, in other words, estimate invariant density, or whatever you want to do, like invariant sets and so forth. So here's the upper bounds for the two, for a given k, for a given data set size. Data set size 10 to the 6. Here's k. The optimal k ends up behaving a lot like theory. This one's computed numerically, and it ends up being very close to what you would estimate by the analysis. And the mean square error at the optimal k for different bandwidths, you can see at different places in the domain X, you get different qualities of the estimate, but these are all pretty small numbers. Like you see, this is down here at 10 to minus 5, it's a log scale. And in kernel density estimation, the choice of bandwidth affects accuracy and bias. So here's the invariant density, the punchline, and various estimators for different bandwidth size, 10 to minus 3, 10 to minus 5, for a data set size of 10 to the 6. But anyway, the error is the important part of this story. Here's for different bandwidth sizes, and for example, this bottom guy, you can see that at a very small bandwidth, you kind of get more variation in the quality of the error, but the error is quite good, still 10 to minus 5. I'm going to skip to the very end, just more pictures that show you that, like, okay, the experiment agrees with the theory. I heard once a joke about applied mathematicians versus pure mathematicians. Pure mathematicians prove a theorem, and they say, great, that was nice. And the applied mathematician says, now I'm going to show you an example that proves that the theorem was correct. And just different versions of pictures of the same thing. So here's kernel density estimators of that kernel, which is the matrix. That's another one of the stories. That matrix, that kernel, is a distribution in its own right, and it is the likelihood function that would correspond to a Bayesian discussion of the story. And the left eigenvectors. So there's a conclusion. Some data-driven error analysis to go along with the data-driven method of operator estimation. And I did this for Frobenius-Perron. I think this also has a role in Koopman, but no one's doing it yet, not even me, because I haven't gotten around to it. So if you want, you can try to beat me to it. We've been doing we've just been estimating these operators for years and years and years without actually discussing the estimate of the quality of your estimate, which there's a method to do that. And the kernel of the operator is a matrix, and the kernel of the operator is there. It's also a density, and I can think of it in the Bayesian terms. And think of estimating the kernel of the operator by kernel density estimations. And there's the word kernel used in two very different ways in the same sentence. And thanks for having me.